Hello everyone, welcome. Today we're gonna solve stresses for a truss using the slope and either maybe trigonometric function. Slope is very easy to use when solving stresses like A, B, AC. All the stresses you can use the slope, and it's more convenient than using the trigonometric function. And if I have time, I can show you the trigonometric function as well. But let's go to the slope. It's better. To use the slope, you have to determine the slope dimensions. Here, the vertical is the height of the truss, and the horizontal is the where the incline member ends up to, and then you draw the line, and that's 3 meters, 4 meter high, and the horizontal is 3 meter. We usually don't know this incline value there for the slope, so we have to solve that. To solve for the inclined slope there is like you extracting draw the triangle ABC right here. ABC. If this is your angle here, that's your opposite side A, and this is the adjacent side B, and this is the hypotenuse of the triangle. To solve for C, so we have to find C. Solve for C is use the Pythagorean theorem. The Pythagorean theorem is given as the formula as C. It is actually C squared plus B squared. Now it is actually C squared is equal to A squared plus B squared. And just make a shortcut here, and to find the C is the square root of A squared plus B squared. So substitute the value of the known component of the triangle of slope here, the 4 and 3, substitute that here. So 4 times 4, 16, and this is 3 times 3 equals 9. Add together is 25. The square root of 25 is 5, so we have the 5 there. So our slope triangle now is 4, 3, and 5. So we can use that all the way to solve for the stresses of our truss. The AB, anything there, AC as well. All of it, we can use the slope triangle. So solving for stresses FAB, FAC, and CB. The force AC and force AB. FAB divided by 5 is equal to 100 divided by 4, and FAC here divided by 3 is equal to 100 divided by 4, forming these two equations here to solve the two members of the truss, the AB and the AC. So forming this equation here, what do you think, what is the name of the process of what we're doing here? We are equating something. What do you think this process here that I'm doing to get these equations here? This is equation 1 and this is equation 2. The answer is simple, and you should always remember this, that this is what you're gonna do. This is all you're gonna do to solve for the stresses of your truss. There we go. Yeah. To form this equation here, these two equations, you are actually doing the similar triangle between the slope and the forces of triangle you have there, A, B, C. The See, the slope triangle is equal to the forces of triangle. So that's why the FAB here, FAB, we're doing a similar triangle. Okay, this is all. This is what you need. This is all you need to solve for the stresses, and you don't get lost when using this similar triangle. It is similar triangle. As long as you get the slope, right away you solve for the slope. See, look at how I do this. FAB, alright, this is the incline, is equal to the slope there, that's just 5. You divide that. FAB over 5 is equal to, and always equate to the known value. The known value here, we isolate joint A, right here, and then transfer the reaction as the vertical force here, BC. So that's your known value, 100. So this FCB here is 100. So equate the FAB over 5, that's the incline, equate to the vertical, which is 100, and the 100 for the slope is, the vertical slope is 4. So FAB over 5 is equal to 100 over 4. And then you know how to cross multiply this. Cross multiplying this, 5 goes here, and 4 remain there. So 5 times 100 divided by 4. FAB now is equal to 125. That's very simple. And now FAC. The FAC here also. FAC here divided by the slope, horizontal slope there is 3, is equal to, again, equate the unknown to the known value. Your known value here is 1, is just BC to 100, the reaction. You transfer the reaction here to form a complete triangle of forces. So we have the 100 right here. So it's equal to 100 divided by 4 right there. And now cross multiplying that, now we get FAC is equal to 100. The 3 here goes here. In cross multiplication, you get 300. Multiply 100 by 3 equals 300 divided by 4. FAC now is equal to 75. Alright, so just that simple. So now to do the similar triangle, you have to isolate the joint A and form a complete triangle with a known reaction transfer to the BC. This is the reaction here. Alright. Okay, now we have that reaction there. Now to that's how simple is the using the slope of your truss. Now how to determine the direction of all forces, either tension or compression. Now to do that, you have to draw the diagram of the triangle ABC. Okay, analyze your forces first, and the reaction is going upward, and therefore this member here AB is going downward to oppose that to maintain equilibrium. To maintain the static equilibrium, AB should be going down, and what is going down is compression, and the tension is going away. Tension is the presentation of the force when it's a tension. The direction of the arrow should be away from the joint, and the compression is towards the joint. See, you plot all these forces here all together in one triangle. This is the presentation of tension. There's two arrows in the middle, okay, whereas the compression is one arrow from one joint and one arrow from the other to the other. So that when you isolate direction of forces, when you isolate joint A, you draw a circle there, you cut the tension there and you cut the compression there. What is left is this. Compression is going towards the joint and the tension is going away from the joint. That is from the whole, this is the whole member, you see. The presentation of tension has two arrows in the middle at the center of the member. That's why when you isolate that, when you cut it right here and cut it right there, and this is compression, what you have is this compression here, arrow, and the tension is away. That's why it is away from the point A. Now we have the horizontal component for 125. If you work it out using the slope, is 75 kilonewton. And if you're looking at joint B here, and since this is compression, and you cut it there, the arrow is going towards the joint. Joint there and joint there. And when you cut it here, the tension is going away from the joint. Now we don't know the direction of this force here, the BC. We can find out by taking moment at A. Alright, so for now we cut our member BC there, and let's assume that this red arrow is the assumption of the BC as tension. It's going downward. Alright, so when this is going downward, according to our first assumption, we can find out by taking moment at A. We can easily find out the direction of the force BC, whether compression or tension. For now, let's assume it's tension away from the joint. That's why there's a red arrow here. That is the assumption. And when this is tension, when you take moment at A, you look at carefully the direction. I assume the clockwise as positive and the counterclockwise is negative. That's the sign convention that I consider. When you assign a sign convention, you have to stick with it all the way up to you complete the solving all the stresses. You never have to change. Okay, you're not allowed to change once you assign the sign convention. You can assign counterclockwise, but it depends on you, positive or negative, doesn't matter. Here I assign clockwise as positive and counterclockwise negative, and so then since we assume this is tension going downward, when you take moment at A, the force BC will also rotate in clockwise rotation, and ABH also in clockwise rotation. This is how you find the direction of the force. You can't really tell the direction of the vertical force here. Here it's easy, this is compression for sure, guarantee, right? And here is tension, because when the load is applied, this will go down. That's why it is in tension, alright? So the vertical there, it's hard to define whether it is tension or compression, and this is how you find the direction of the vertical member of your truss. Okay, now that's tension, and all the way we rotate this. So therefore summation moment at A is equal to 0, and the clockwise positive, counterclockwise negative. 75 is going clockwise, the lever arm is 4, 75 times 4, and also BC we assume as its tension. Also we're going clockwise, so it's positive 3. The lever arm for BC is 3 meter. So 3 plus 3 BC is equal to 0. That's the first equation of equation 1 of the condition of equilibrium. Now the 75 times 4 is 300, and 3 BC is equal to 0. 3 BC now, to solve for, there are two members of the equation here, the 300 and the 3 BC. You have to transpose any one of them. I would like to transpose the 300 to the other side of the equation right here. Alright, so when you transpose one member of the equation to the other side of the equation, you have to change the sign. So this negative, positive becomes negative. So 3BC now is equal to negative 300 over 3. You divide both equations by 3. Divide this by 3, it becomes BC, and 300 divided by minus 300 divided by 3 is equal to 100 kilonewton, and it's negative. To divide two numbers having unlike sign is absolutely negative. Alright, so this is negative 100, and therefore, and since we get negative here, that is opposite to our assumption. So the assumption that we have here downward is wrong. It's actually upward, which is compression. Here's the correct assumption. Assume this to be compression going upward, and when you take a moment at A, the ABH is going clockwise rotation, and the BC is going counterclockwise. So we have an equation like here now. 75 times 4, that is a clockwise rotation, and the BC, since we assume it's compression now, it's equal to minus, it's a counterclockwise. 3 BC is equal to 0, equation equilibrium number 1. This is 300, and this is minus 3 BC is equal to 0. Again, to solve the unknown, we have to transpose one member of the equation. Transposing 3 BC to the other side of the equation becomes positive. 3 BC now is positive, is equal to 300, and the 300 will remain the same positive. It's 300 divided by 3, both side of the equation divided by 3 becomes BC here, and this is positive 300 by 3 divided by 3 is equal to 100. And to find the direction of the force, when you get negative like this one here, always remember this. But be careful with this sign convention and look at properly the rotation of your forces. When you get negative, your answer here, meaning your assumed direction is wrong. So this is wrong, the tension is incorrect, and this is the correct one. And when you see negative there, just reverse the assumption there. It is actually compression. This is the right one. See, BC is equal to positive. Positive means agree. It's not. It doesn't mean tension or compression. It is the agreement of the sign convention. When you get positive, meaning yes, it is going upward. The negative and positive here is the yes or no with respect to your assumption. It's not It's not the tension or compression, it is the yes or no. This one here is a no, it's negative. No means the tension here going down is wrong, and it is actually going upward, and it is compression. So that's how you get your direction of forces. And the horizontal member here is easy. If you have to analyze your forces as well. See that here? You have to have your own analysis first. You always start with the reaction because that's the known value there. See, when the load is applied, this load pushes this bottom core down. You're gonna have deflection right here like that. So therefore, when deflection is going down, these members here, all these members here, will sustain a tension. Since it is restrained here, fully restrained, it's not gonna move. And here, so when this load is applied, there's a tension going on here. And that's why the BC is kind of, we don't know. We can only find out the direction of BC is by taking moment at A. Alright, in here the AC is, you can analyze it, by inspection. When the load is applied, this bottom core here will be stretched, so it is tension. The presentation of tension, as I said, has two arrows at the center of the member, and for compression, the arrow is at the joints, so both joints. So to isolate the joint, any joint, when it is compression, the arrow is going towards the joint, and the tension is away. Alright, so this is the presentation, the explanation of how your forces in terms of direction. So yeah, this is the slope. It's pretty easy, and you can solve all the stresses here using the principles that I gave you. And since this, if you look, you analyze your truss too. Since this is symmetrical load, symmetrical in distances, right here, therefore only half of this is equal to the other half, so only solve half. And I think maybe this one also is equal to this one. The force here is 125 as well, but I don't know, you have to solve it yourself. So at the joint B here, there is BD, the BD right there, and since this is compression, also the BD, the force right here, also going towards the joint to maintain equilibrium. Always think about equilibrium, equilibrium of forces. When this is horizontal here going to the right, the next structural member should be going to the left. And also, if you take summation of moment horizontal, BD right here, right there, BD also is equal to 75, guarantee that. And even here, horizontal forces, 75 right here too. This is 100. This is pretty easy demonstration of the truss. Alright, so everything you have there, you can solve the whole truss if you want. And I guarantee you all these members here is same as this, the half. You only solve half, and then all the stresses there are the same. They are equally and symmetrically loaded, and distances as well. Alright, there you go, the slope and here's one more more thing here, the reaction. The FCB right here is equal to RA. That's why I transferred it here. So to prove that this is 100, so that you didn't get confused why I transfer the 100 reaction there to complete this triangle. To prove that is this, to prove that they are equal, the CB and RA are equal. To prove that they are equal, use the, now you can use the force FAB, which is 125. And by again using the similar triangle of the slope and the triangle forces, we can use the known value now, 125, the FCB right here divided by 4, the slope, vertical slope, is equal to 125, the incline, divided by 5 right here. FCB now is equal to 125, 4 goes there, it's equal to, and divided by 5, FCB is equal to 100. See, they're all correct. See, you verify that when you transfer the, you can transfer the RA to complete the triangle right here. Alright? Alright, thanks for watching, and don't forget to subscribe. Your subscription is important this time, actually, because the YouTube changed the requirements for creator like me to upload videos and to remain in YouTube. You need 4,000 hours of view time and 1,000 subscribers. That's a lot. Alright, anyways, see you next time for the next video. Thanks.